Good afternoon, everyone. Can everyone hear me? How are you guys doing? Pretty good. Last day of classes, right? So let's wait another minute or two and see who else will join. So why do you say something on Friday? According to the UP academic calendar, classes should end today. So I was just told to show up to class. Okay, that's interesting. That's very interesting. So, for today's lecture, we are going to end off this semester by speaking about astrobiology. Or astrobiology can rather be defined as the study of life on other planets. So, for this lecture, we are going to talk about nature of life, life in the universe, as well as intelligent life in the universe. So for this lecture, we need to answer four important questions. One, what is life? Secondly, how did life originate on Earth? Thirdly, does life exist on other worlds? And lastly, can humans communicate with intelligent beings on other worlds? So to put this into a bit of perspective and to give you a few things to think about, I'm going to show you two videos. One is of Dan Wertheimer. He is from the University of California, Berkeley. And the other one is also from Berkeley. It's from Andrew Simeon. So Andrew Simeon is the director of Breakthrough Listen, and Dan Wertheimer is the chief scientist of SETI. Are you guys familiar with SETI? So SETI stands for the Search for Extraterrestrial Intelligence. So I've spent a lot of time at the University of California, Berkeley. I also know Dan Wertheimer and Andrew Simeon pretty well. I had some fun discussions with them over a bottle of wine on the roof of the astronomy building at Berkeley. So let me show you these two videos.
Thanks very much. So I want to talk to you about this question, are we alone? Is anybody out there? It's a question that humans have been asking for a few 100,000 years. And maybe in this century, we have a chance of answering the question. The field is called SETI, the Search for Extraterrestrial Intelligence. And there have been lots of ideas over the years about how we might get in touch with ET. Some of the early ideas, Gauss, the mathematician, suggested that we get in touch with ET by making large geometric structures on the planet, a right triangle, maybe 3, 4, 5 miles on a side, a big square of dirt, a big square of water, and a big square of wheat. And ET would look down and see that we knew about the Pythagorean theorem, and maybe they would get in touch. It was a great idea at the time. Unfortunately, it was not funded. And then Charles Crow suggested that we get in touch with the Martians by, I'm sorry. He suggested we get in touch with ET by digging a circular ditch 20 miles across and fill the ditch with kerosene and then use this match, not to scale, to make a bright circle of light, a bright circle of fire. And then ET again would look down and see this bright circle. and maybe they would get in touch. And I think you might be able to guess what happened with this. Met with a similar fate. And then Charles Crow suggested we get in touch with the Martians by using large mirrors to reflect the sunlight to the Martians, actually several mirrors, one where he lived in Paris and the others to outline the shape of the Big Dipper. And I think you guess what happened here. The first funded project in SETI was to send pornography into space. So this is a plaque. You might have seen it on the Pioneer 10 spacecraft that left the Earth in the early 70s. And these are very controversial. Originally, they were holding hands. And NASA decided that that was not a good idea because ET, if they found this plaque, they would think it was one creature. So they don't hold hands right now. And here's the solar system and the sun and Mercury, Venus. And here is Earth. And you can see the spacecraft leaving the Earth, traveling at about 100,000 miles an hour, going out to the stars. And then these are directions. This is a map so that if ET wants to know where we live and they want to come and eat us, they'll know exactly where we live. So that was the first funded project. One of the big questions in SETI is, are there good planets out there going around other stars? And if you had asked me 20 years ago, are there planets going on other stars? I would have said, I don't know. Nobody knew at that 20 years ago. But that has all changed, largely due to work here at San Francisco State University. They pioneered how to find these little dinky planets. Planets are hard to find because they're little, they're very tiny. 1 million Earths could fit inside the sun. And they're right next to this really bright thing. So they're really hard to find. And that work was pioneered here, and it led to this thing called Kepler, which the way that Kepler found planets was to look and see if a planet goes in front of a star. I don't know if you see this little black dot here, but that is a planet going in front of a star. And you can't actually see the planet from the Kepler spacecraft, but what you can see is that the light dims down a little bit. When the planet gets in front, the light dims down. If you see a star that dims down a little bit, you say, what's going on? Well, that betrays the presence of the planet. And if it goes around periodically, every few months or every year or whatever, then you really know that you found a planet. And Kepler found thousands of planets. And here's an example of some of the planets going around their stars. And you can see that a lot of the planets are in multi-planet systems, 6, 7, 8 planets. And now we know that there are more planets than there are stars in the Milky Way galaxy. There are about 1 trillion planets in our Milky Way galaxy. And if you're not happy with the trillion planets, there are about 100 billion other galaxies besides the Milky Way galaxy that we live in. A lot of places, and a lot of those planets are little dinky things like Earth, little rocky planets, and we think a lot of them have liquid water. We call them Goldilocks planets. If the planet is too far from the star, it's going to be cold. If it's too close, it's going to be too hot. If it's at the right distance, it's a Goldilocks planet. Okay, we have a lot of planets. Well, what about life? How often does life get started? We don't really know. We don't understand all the details of how the chemistry turns into self-replicating molecules. But we are optimistic about primitive life. And the reason we're optimistic is because life got started on Earth very early. The oldest rocks you can find have microfossils. As soon as the Earth cooled down, it looked like life popped up. So even though we don't understand the details, because it happened quickly here on Earth, we think it's going to happen quickly on other planets as well. And so the universe is probably teeming with simple life. We don't know how often it evolves to become intelligent and teeming with simple life. There may even be life in our own solar system. So this is a moon going around Jupiter called Europa. This is a cutaway view. And you can see that it has a liquid ocean. This blue stuff is liquid water. It's heated by tidal forces. And maybe there's something swimming around down there in the ocean. The problem is we can't tell because this white stuff is ice. It's covered with ice. Even though it's warm water, it's covered with ice. It's about 30 miles thick of ice. And we don't know how to get through the ice. So when I give talks at elementary schools, I ask the kids, how are we going to get through the ice? And I tell them we don't really know. NASA doesn't know how to do it. And the boys have a different answer than the girls. The boys say machine guns or bombs. They're kind of like Donald Trump. And the girls are usually a little more clever and not as violent. They want to melt their way through the ice, like use mirrors to focus the sun's rays and heat the ice. Anyway, it's interesting at elementary school already. There's a kind of separation there, unfortunately. Okay, so there's a lot of other moons, and even in our own solar system, we might find primitive life. What about how are we going to find intelligent life? So one of the ideas is that Earthlings are sending off a lot of radio and television out into space. And we've been transmitting television signals now for about 70 years. The early shows, like I Love Lucy and Ed Sullivan, have been traveling out. Now they're 70 light years out. They've gone past about 10,000 stars. And the nearby stars have seen The Simpsons. So they haven't seen Donald Trump yet. So this is a plot of television power leaving there at 1940, 1950, 1960. And you can see we're getting brighter and brighter. And we're brighter than the sun now at television frequencies. So if we are transmitting messages that go out traveling at the speed of light, much faster than our rockets, maybe ET does that too. And we've even sent messages intentionally. This was a message transmitted in the 70s. We think that pictures are a good way to communicate. They're not going to speak English or Portuguese, but we think pictures, images they're going to be able to perceive their environment or 2 or 3 dimensions. And so this was a picture with a person and a DNA molecule and the solar system. Maybe you can see the sun and Mercury, Venus, and the Earth tipped toward the person, a radio telescope. Anyway, that is an example of how you might start up a conversation. Math is another good way. Prime numbers, 2 + 2 = 4, stuff like that. Okay, so we are sending off radio signals out into space. We want to find out if ET's doing that too, if they have television or radar or radio. So in order to do that, we need a big radio antenna. We call them a radio telescope. This is a one that we started using in the 70s. It's 85 feet across. And while we were using this telescope to look for ET, this is what happened to it. This is the dish. It used to be up here on the pedestal. So we moved to a different telescope. We moved to this telescope. This is another radio telescope in West Virginia. This is 300 feet across, one of the world's largest telescopes. And while we were using this telescope to look for radio signals from ET, this is what happened to that telescope. And you might ask, why did that happen to Dan? Why did both telescopes that he was using to look for ET get destroyed? Well, the answer, according to the World Weekly News, is that the aliens did not want to be discovered, and they zapped the telescope, zapped by hostile space aliens. So we're testing this idea, the ZAP idea, at this telescope. This is the world's largest radio telescope. It's in Puerto Rico. It's 1,000 feet across. It's called the Arecibo telescope. It holds 10 billion bowls of cornflakes, although we haven't actually tried that yet. So far, it has not been zapped by hostile space aliens. Although it's a little harder to zap. You might have seen it in the James Bond movie GoldenEye, although in GoldenEye they say it's in Cuba, which is not, and it comes out of the water, which it doesn't. But it was also in the movie Contact, which was a book written by Carl Sagan, who used to work in our group. Anyway, so we collect a huge amount of data at this telescope, petabytes, many petabytes of data. And the problem we have is that it's so much data, we can't analyze it all ourselves with the computers that we have, even the supercomputer that we have at Berkeley. So we are asking volunteers all around the world to help us. If you have a computer, a laptop, or a desktop, or an Android phone, you can help us analyze the data. And the way it works is that we store the data, and then we break it up into little pieces. So if you want to help us analyze the data, you run a little screensaver program called the SETI at Home Screensaver Program. You download this free program. If you want to find it and help us look for ET, Google SETI, S-E-T-I, and you'll find SETI at Home, and you can download this program. And you can volunteer to help us analyze the data. And the way it works is that everybody gets a different part of the sky. So you'll get one part of the sky, you'll get a different piece of the data. And then when you go out for a cup of coffee, the screensaver pops up on your computer, just like but instead of just putting pretty pictures of goldfish swimming around on your screen, it's actually going through the data that you've been assigned, looking for all the different frequencies and signal types. And when it's done, it might take a few days, it'll send the results, whatever you find, whatever your screensaver finds, any strong signals it finds, it sends the results back to our computer at Berkeley, and your name is attached to that data. So if you find ET, you get the Nobel Prize. Although it's actually not mine to decide, but you might get it. This is a little animation of the data that's going out from Berkeley to all the volunteers around the world. The yellow dots are the data that we're sending out. The blue dots are when they're finished analyzing the data, then they send back the results, and they form one of the biggest supercomputers on the planet. There are about 8 million people who are helping us out. They're spread out in 226 countries, and it's made the search incredibly sensitive and much more powerful beyond our wildest dreams, and we're very grateful to the SETI at Home volunteers. And I hope if you're not running SETI at Home, you'll go and download this thing and help us look for ET. The software that we developed, the SETI software, is open source software, and it's being now used by a lot of different science projects. So you can, at home now, instead of just doing SETI, you can look for malaria drugs and cancer drugs and HIV drugs. This is a program you can run to search for black holes. This is global warming, climate prediction. This is looking at pulsars and gravitational waves. This is protein, and you can allocate how you want your computers to be used. You can say, I want 20% of my spare computing cycles to go for SETI and 30% for malaria research. And you can participate in your favorite projects. So this is a brand new thing that we're doing this year. We ran into a billionaire and the Breakthrough Prize Foundation, and they gave us a lot of money to do a huge SETI program, and we're just starting with 3 telescopes. In fact, one of the telescopes that we're using, we're just launching today. So we've started using this thing at Lick Observatory, looking for laser signals. Lick Observatory, some of you might know, is near San Jose up east on Mount Hamilton. And we're looking for laser signals there. And then we're using a telescope. The one that collapsed in West Virginia, they built a new one, and we're using this one in West Virginia. And then the thing that we're launching today that we're really excited about is a telescope in Australia called the Parkes Telescope. The reason we're all excited about this thing that we're starting today is that if ET's lurking in the south, these other telescopes that we've been using are in the north. So if it's one of the southern stars, we would have missed them. And this is very little work has been done in Australia and looking at the southern stars. So we're really excited about that. We're going to look at 1 million stars and 1,000 galaxies. It's a big, new, powerful project we're really excited about. Another thing that we're excited about is a brand new telescope that's being built in China. This is going to be even bigger than the one in Puerto Rico. It's 500 meters across, and you can see it's made out of little panels. And now it's all finished, and they're just starting to use it, and we're hoping to work with the Chinese to do SETI. This is kind of longer term, 10 or 20 years away. We're learning how to build, instead of one big dish, build a telescope out of lots of little dishes, maybe thousands of little dishes. And this is being built in South Africa and Australia. A lot of countries are getting together. And we think that'll be a spectacular way to look for very faint signals, making a giant telescope out of lots of little telescopes. The other thing we're excited about is that computing power is getting better and better. A lot of you know about Moore's Law. And right now, this is a plot of computing power as a function of time. And right now, computers are about as smart as a lizard or a guppy. If this trend keeps going, computers will be as smart as humans in about 30 years. That's called a singularity. Watch out. Could be good, could be bad. But in any case, we will be able to do some very good SETI experiments. Right now, we're just getting in the game. We're learning how to do it. We can't do all the frequencies and do a thorough search. But if computing power keeps going and the telescopes keep getting better, I'm optimistic in the long run. If there are radio signals out there, could be found maybe in your generation, maybe in the next generation. Okay, if you've been asleep, this is really the only slide you have to remember. No ET so far. We're still working on it. However, that is not my last slide. I've got 3 more. So I wanted to tell you a little bit about the SETI at Home volunteers. The SETI at Home volunteers have helped us enormously. They built one of the biggest computers on the planet, made a very sensitive search. But they also help us write the software. It's a big open source project. They help make it go faster, port it to new platforms. They just got it working on Android. They get the bugs out. They also send us money. The donations come from the volunteers, which is great because it keeps the students working on analyzing the data, keeps the students fed. Then they also send in literature and music, and some send haikus. And thousands of people have sent us haikus about SETI. But don't worry, I'm not going to read you thousands of haikus. I'm just going to read you a couple of haikus. So Paula Cook at Duke University, searching for life, answers are revealed about ourselves. And this is the last slide, the last haiku. 1 million Earthlings, bounded by optimism, leave their PCs on. Well, thank you very much.
Good morning. Are we alone? Do we live in a universe that is populated with many, many intelligent species? Or are we, as human beings, just the only intelligent life anywhere in the universe? The last couple of centuries have been a triumph of modern astronomy. We can now trace back the history of the universe to just seconds after the Big Bang, when our universe began. We can watch the cosmic microwave background and map out the structure of the very early universe. We can track the very first stars that formed in the first few hundreds of millions of years after the universe was born. We can track the formation of galaxies. We understand nearly everything that there is to know about the way that the universe was born and the way that the universe continues to evolve, except for one very glaring exception: life. We know that in the very first few hundreds of millions of years after the Earth formed, life arose on our planet. We know that from fossils like these, stromatolites, that were formed by the very first organisms that existed on our planet, cyanobacteria. So very, very quickly, as soon as the Earth cooled off after its formation, we know that life began here. And even more amazing than the fact that a self-replicating organism somehow came forth amidst the laws of thermodynamics that govern our universe, that life evolved fantastic complexity, and in fact, eventually evolved intelligence. Amazingly enough, we now know that nearly every single star in our galaxy hosts a planet. And something like 1 in 5 of those stars hosts a planet something like the Earth, at just the right distance from the star to have liquid water exist on the surface. But on any of those planets, did life arise? Did something similar to what happened on our own planet happen on those other planets? We know that the galaxy is awash in water. It's awash in organic molecules and complex chemistry. All of the things that we know were necessary for life to begin on this planet exist in abundance throughout the galaxy. But did life ever arise on any of those planets? And even more pressing of a question, did that life, if it did arise, did it ever go on to develop intelligence? Is intelligence a common outcome of life? Is intelligence a driven process? Does life proceed towards intelligence for some reason that we don't yet understand? Or is intelligence simply some evolutionary fluke that only happened on one single planet that maybe did develop life? And again, even more interesting, if intelligence does arise commonly, how far can technology progress? How advanced could very advanced life become? The universe is nearly 14 billion years old, and our galaxy is something like 12 billion years old. So there could be life out there if it's that could be dramatically more advanced than the life that we have here on this planet. Now, we don't have any way of directly detecting intelligent life, so we use technology, or can use technology, as a proxy for intelligence. Here on this planet, we have been producing technology that has been emitting signals that would be detectable at very, very large distances, well out into the galaxy, for hundreds of years. These are things like high-power TV and radio transmitters that we use for communication systems here on Earth, radars that we use to map other planets in our solar system, or asteroids that we have in our own solar system, and also laser technology. Now, we don't do this yet here on our planet, but it's an amazing fact that if you take our most powerful lasers and our largest mirrors and you pair them together, for the fraction of a second that our most powerful lasers can produce light, they can outshine the sun by factors of 1,000 at more than 1,000 light years away. We have just announced a brand new program that we think is going to be humanity's best chance ever to answer this question. It's called Breakthrough Listen. It's humanity's boldest attempt ever to determine whether or not we are alone as intelligent beings. It's a $100 million 10-year project that will use 3 telescopes to conduct the most comprehensive, sensitive, and intensive search for extraterrestrial intelligence in history. We're going to use optical telescopes, one called the Automated Planet Finder that is just about an hour away from here near San Jose at Lick Observatory, and 2 of the world's largest radio telescopes, the Parkes Telescope in Australia near Sydney, and the Green Bank Telescope in West Virginia here in the United States. The Green Bank Telescope is one of the world's largest movable structures, and it is in fact the largest fully steerable antenna that we have here on this planet. With a telescope like the Green Bank Telescope, we could detect a human-like technology nearly to the center of the galaxy. We're going to search a variety of different types of objects. We're going to conduct a survey of 1 million stars within about 1,000 light years or so of the Earth. We're going to conduct a comprehensive survey of the entire plane of our Milky Way galaxy, and we're going to search 100 nearby galaxies to see if that very, very advanced life might have developed the necessary technology to transmit at truly extraordinary distances between galaxies. Let's take a look at how that's going to work. Here's an animation of the Milky Way galaxy. Imagine that somewhere in the Milky Way galaxy, intelligent life arises and begins to transmit. If they did so, their transmissions would proceed at the speed of light out from their star for as long as that intelligent life existed. And that would form a bubble of electromagnetic radiation that we might be able to detect here on Earth. But how long do these civilizations live? They might develop life, intelligent life, and then some technology and a radio signal, but that radio signal will only continue to emit for as long as the civilization lives. But these bubbles of electromagnetic radiation continue out into the galaxy at the speed of light. And here on Earth, we can potentially detect those with our very, very large radio telescopes. So here's the Earth itself transmitting electromagnetic radiation, radio signals, and here are these bubbles of radiation from signals from other intelligences that are sweeping across the Earth. And we can detect those, again, with telescopes like the Green Bank Telescope here, and this is an animation of the signal that we might expect to see from that civilization, and also with the Parkes Telescope in Australia. And it's not just us that's going to be doing the data analysis. With Breakthrough Listen, there is a very key component of the program that will make all of the data that we collect available to the public immediately. It will, in fact, when complete, be the largest amount of scientific data that's ever been made available to the public for any experiment whatsoever. And this is one of the ways that you can get involved in that program with an application developed here at Berkeley called SETI at Home. This is a program that you can download on your computer, and when you're not using your computer, when you're getting up to get a cup of coffee, if you take long enough, your computer will wake up, it'll download a little bit of the data that we collected at these giant radio telescopes, and use your computer to do the very computationally intensive processing that's required to detect these very weak signals that we're looking for. And your computer will join with hundreds of thousands of other computers and will in fact form the largest supercomputer on the entire planet Earth, dedicated solely to hunting for evidence of extraterrestrial intelligence. And here's a video showing how this process works. Here we see at Berkeley, California, where we all are here, all of the data that we collect from these telescopes being sent out to hundreds of thousands of volunteers, and then results of those computations being sent back to us at Berkeley. And if one of those little blue dots comes from your computer and happens to contain evidence of extraterrestrial intelligence, you too will share in the Nobel Prize that we will surely win. But I warn you, you have to share it with the hundreds of thousands of other volunteers that participated in the project. So you might only get a couple of nickels. But surely it would be one of the most remarkable discoveries in the history of humanity. So I wanted to take a minute to look back briefly at one of the still images from the video that I showed you to point out something very, very remarkable about the search for extraterrestrial intelligence and something that we do in this science. So here we see the bubbles of electromagnetic radiation coming out from the civilizations that may exist somewhere in our Milky Way galaxy. And these bubbles of electromagnetic radiation, they have fixed widths. They don't, they're not constant. And that reflects the lifetime of the civilizations that might be arising. And this is something that's captured in a very, very famous equation in this field called the Drake equation, named after Frank Drake, one of the pioneers of this field. And I promise that this is the most complicated bit of mathematics that I'll show you today, but I think it's worthwhile to take a minute to walk through this. So this equation here, n, is the number of civilizations that we might be able to detect. And it's expressed as a product of all of the factors that might go into the emergence of intelligent life. R star, the rate of star formation in our galaxy. Fp, the fraction of those stars that have planets. Ne, the fraction of those that are something like the Earth. Fl, the fraction of those that actually develop life. Fi, the fraction of those that actually go on to develop intelligence. Fc, the factor of those intelligent species that go on to develop some kind of communication technology that we might be able to detect. But perhaps the most interesting factor in this equation is L, the lifetime of the civilization. How long can an intelligent, communicative civilization actually exist? Now, if we look at our own technology and our own human society, we might ask the question, well, maybe not very long, maybe only a few hundred years. Can a truly advanced technology exist for thousands and thousands of years without destroying themselves? This is something that we're able to probe directly in our experiments to search for intelligent life. We're now just beginning to explore the area around our own planet. In 100 years, surely the area around our planet is going to be populated with innumerable satellites, communication technology. Perhaps we'll visit the moon again. Perhaps we'll have a colony on Mars. Maybe in 1,000 years, we might actually have permanent colonies in space. We can sort of imagine getting that far with our own current technology. But where might we be in the far future? Can we, as human beings, exist long enough to actually travel between the stars? Could our technology progress far enough that we could actually become an interstellar civilization sailing between the stars on giant spacecraft? This is the ultimate question of the search for extraterrestrial intelligence. We're searching for life beyond the Earth, but truly what we're searching for is our own future. We're asking the question, what is the future of an intelligent civilization? How long can they last? This is something that a pioneer in this field, Philip Morrison, called the archaeology of the future. Because of the finite speed of light, we're studying civilizations that as they were 1,000 or maybe 10,000 years ago. Our galaxy is 100,000 light years across. So if we detect a signal from a civilization that is on the other side of the galaxy, we're seeing that civilization as it was 100,000 years ago. But because our galaxy is so old, many billions of years, it's likely that that civilization we detect is much, much more advanced than we are and has been around much, much longer. So although we're looking at that civilization's past, we may be looking at our own civilization's future. Thank you.
So what are you guys' opinions? Everyone's still awake? So why do you say, why should we leave ET alone? So you won't get more than the beginnings of answers to those questions here. But often in science, asking a question is more important than getting an immediate answer. You have explored the universe from the phases of the moon to the Big Bang, from the origin of Earth to the death of the sun. Astronomy is meaningful, not just because it is about the universe, but because it's about you. Now that you know astronomy, you see yourself and your world in a different way, and astronomy has changed you. As a living thing, you have been promoted from darkness. The atoms of carbon, oxygen, and other heavy elements that are necessary components of your body did not exist at the beginning of the universe, but were built up by successive generations of stars. The elements from which you are made are common everywhere in the observable universe, so it is possible that life began on other worlds. Future explorers may find alien species different from any life on Earth. It is possible some of those species have evolved to become intelligent. If so, perhaps those other civilizations will be detected from Earth. Your goal in this chapter is to try to understand truly intriguing puzzles. The origin and evolution of life on Earth and what that tells you about whether there is life in other worlds. This new hybrid field of study is called astrobiology. So what is life? Philosophers have struggled with that question for thousands of years, and it's not possible to answer it completely in one chapter or even one book. An attempt at a general definition of what living things do, distinguishing them from non-living things, might be: life is a process by which an organism extracts energy from the surroundings, maintains itself, and modifies to foster its own survival and reproduction. One important observation is that all living things on Earth, no matter how apparent different, share certain characteristics in how they perform the process of life. The physical basis of life on Earth are carbon and water. Because of the way carbon atoms bond to each other and other atoms, they can join into long, complex, stable chains that are capable, among many other feats, of storing and transmitting information. A large amount of information is necessary to control the activities and maintain the forms of living things. And all living things on Earth, the chemical reactions making, breaking, and combining carbon chains, take place in liquid water within the cells of living organisms. So in this image, we can see all living things on Earth are based on carbon chemistry in water. So that is why usually in sci-fi shows speak about we are carbon-based life forms. So if you look at a periodic table, the elements in the periodic table that's in columns are grouped together and are of the same kind. So which is the next element below carbon in the periodic table? Any suggestions? That is silicon. So it's also theorized and perhaps proposed that silicon life forms may be developed on other planets. The reason on Earth it's carbon-based is carbon interacts easily with other elements, and it creates quite stable molecules. The same can happen with silicon. So what is needed for life is the information storage and duplication that needs to happen. So actions performed by living cells are carried out by molecules that are built within the cells. Cells must store recipes for making all those molecules, as well as how and when to use them, and then somehow pass the recipes on to their offspring. So notice 3 important points and 7 new terms. The chemical recipes of life are stored in each cell as information on DNA molecules that resemble a ladder with rungs composed of chemical bases. The recipe information is expressed by the sequence of the rungs, provided instructions to guide specific chemical reactions within the cell. The instructions stored in DNA are genetic information passed along to offspring. So DNA instructions normally are expressed by being copied into a messenger molecule called RNA. The RNA molecule travels to a location in the cell where messages cause a sequence of molecular units called amino acids to be connected into large molecules called proteins. Proteins serve as the cell's basic structure molecule or as enzymes that control chemical reactions. The DNA molecule reproduces itself when a cell divides, so that each new cell contains a copy of the original information. The sequence of DNA that composes one instruction is called a gene. Genes are organized into long coiled chains called chromosomes. The genes linked on one chromosome are normally passed to the offspring together. To produce offspring, the cell must be able to make copies of its DNA. Surprisingly, it is important for the continued existence of all life that a copying process includes mistakes. So speaking about this and a bit off topic, do you guys know what cancer is? So what a cancer cell actually is, or how a cancer cell forms? Yes, it's when the reproduction goes wrong. So what happens with a cancer is the RNA sequence comes wrong. So the RNA tells the message of how the cell needs to duplicate itself. And during that process, the RNA message gets mixed up and it creates a cell that's not specialized into something. So usually different cells needs to do certain things. Let's take your skin, for example. Your cell specializes to create skin molecules. So with cancer, the RNA process goes wrong and it tells the cell to duplicate, but in a wrong way, and it creates a tumor. And as the tumor becomes big, so as a tumor forms, it's basically a cell that's not specialized. So in small amounts, it's not dangerous. But as soon as it becomes bigger, it can cause damage to other organs around it. And that is why cancer is such a big problem. And that is why we need to find ways to stop the RNA from changing its message. So currently that is a combination of chemo and radiotherapy and radiation therapy. But yes, that's where a lot of research are being done. So that's a bit of a topic. So also, let's go back to that as well. One thing that we can do nowadays, and the Nobel Prize for Medicine, I think it was 2021 or 2022, is we know where certain genomes are located. For example, eye color, hair color, physical characteristics. So now you can actually get designer babies. So if you have enough money, by making use of the CRISPR process, you can actually modify your unborn child to pick what its hair color should be, what its eye color should be, what its physical traits should be. And there's a big ethical debate going on around it. So what are your guys' opinions about designer babies and giving you the opportunity to change those features, but it also gives you the opportunity to fix genetic diseases before the child is born? Anyone has an opinion about that? No, so there will be no long-term negative effects. I agree. So then there's people in the same argument that argues then people are starting to play God. I don't agree with that, because with that is you can change genetic diseases. So for example, if you detect that your child will perhaps have Down syndrome or something like that, you can fix it and make sure your child is born normally. And then on the other hand, yes, you can make sure you get a super athletic children as well. But then we can get into eugenics. There are no perfect person, but this could lead to those issues. Yes, exactly. And that is why there are now debates in ethics going on around this, where people are debating this and trying to find a legal framework of how to handle this. But that is just a topic on the side. So Earth's environment changes continuously. To survive, species must change as their food supply, climate, or home terrain changes. If the information stored in DNA could not change, then life eventually would become extinct. And a process by which life adjusts itself in changing environment is called biological evolution. And evolution is still continuing around us. Can you guys think of three recent changes in the human body that shows us that evolution is still a continuing process? So one thing is, let me ask you guys this: who of you had your wisdom tooth removed? So something interesting. If you go back about to when I was young and the generations before that, um, wisdom tooth is a problem because there's no more space in your mouth when your wisdom tooth comes out. And when you look at the biological need for wisdom tooth, it is used to tear down plant material. So right now we are not eating plants that's unprocessed, so meaning plants from directly from trees or the plant itself. So therefore we have no need for wisdom teeth anymore. And the same with a appendix. An appendix, its original function is to help digest plant material that is not refined. Now with our refined diets, we have no need for a appendix. So right now, currently, newer generations or younger generations now are born without wisdom tooth and is born without appendices. And that is part of evolution. So vitamin C, we used to produce it, but because of fruit no longer needed, so it was evolved out. Yes, that is also part of it. And one thing is that in younger generations are now also realized with evolution. If you look at your fingers, depending on which is your dominant hand, on your dominant hand, usually your ring finger or your middle finger will have a slight bump into it. And that bump is to hold your mobile phone more comfortably. And that's also part of evolution. So that shows us evolution is still happening all around us. So here, how that usually works is, so let's say, for example, you are the first person with that specific gene that has changed. So that's called a mutation or a mutant. So usually a mutation. And as it goes on, usually in nature, as the environment around us changes, the normal gene will die out and the mutated gene will continue on, and that will cause that gene to become the prominent gene. And climate change and around us is a big factor of how we are evolving. So back in 2012, 2013, NASA actually did an experiment on epigenetics where they had two identical brothers. They sent one to the International Space Station for a year, and they kept the other one here on Earth for a year on ground. And afterwards, they studied both of their DNA. And you can actually see how weightlessness in space has changed the one brother's DNA a little bit. And you can actually go read up about it. What they call the Kelly brothers. The one who was in space for a year is astronaut Scott Kelly. So what this comes down to is called natural selection. So you guys familiar with the term natural selection? Awesome. So natural selection will shows us that the prominent genes, so the genes that make sure are the ones that continues and you provide to your kids. So it is a common misconception that evolution is random, but that is not true. The underlying mechanisms creating variations with each species may be random, but natural selection is not random because progressive changes in a species are directed by changes in the environment. Life as we know it consists of just a single example of life on Earth. It is okay to think of all life on Earth as being just a single type of life because, as you learned in a previous section, all living things on Earth have the same physical basis, the same chemistry, and the same genetic code alphabet. So how life began on Earth and the development and evolved into its present variety is the only solid information you have to work with when considering what might be possible in other worlds. Everything currently known about life on Earth indicates the same natural process should lead to the origin of life in some fraction of other planets with liquid water. If there is life in other worlds, does it use DNA and RNA to carry the information for the processes? Or different molecules playing the same role, or some radically different scheme? There is no way to know unless another example of life is found on another world. And if and when that day comes, even if the non-earthly life is simple one-celled organism, discovery will be one of the most important in the history of science. It will complete the journey of human understanding begun in the Copernican revolution of progressive realizations that Earth is not unique. So, when we start looking at this, we can see that it is obvious that a 4.5 billion chemical basis that makes up DNA did not come together in the right order just by chance. And the key to understanding the origin of life is picturing the process of evolution running backward. The complexity of environmental factors with the DNA of generation after generation of organisms drove some specialized creatures alive today. Imaging this process reveals in reverse leads to the idea that life on Earth began with extremely simple forms. And biologists that have the first living things would have been carbon chain molecules able to copy themselves. And of course, this is a scientific hypothesis which you can seek evidence. But what evidence exists regarding the origin of life on Earth? So the first thing we can look is called stromatolites. And those are fossilized remains of colonies of single-celled organisms. And we can see and find stromatolites that is 3.5 billion years old. So there are a bit of evidence for that is. And we can also find evidence that we can have single-celled organisms that lived on Earth about 1.2 billion years after Earth has formed. So this image is a fossilized stromatolite in Western Australia that has been found, and it seems to be more than 3 billion years old if you imply carbon dating. So one way to see where life on Earth began happened in 1952, and the experiment was conducted by Stanley Miller and Harold Urey, and this was known as the Miller-Urey experiment. So what they did is they created a closed environment and they stacked it with building blocks of different molecules. So in their molecules, they used normal organic molecules. They have hydrogen, water, and so on. They put it in here, they sealed it, they provided a spark discharge, so to get energy, and they left this to run. And then after a while, it formed basic organic molecules and enzymes and proteins. And that showed that just with the basic building blocks such as ammonia, carbon dioxide, water, and hydrogen, and you give them a little bit of energy, you can create the basic building blocks of life. And then people said, okay, but that's not, can be true. So what would cause the spark? Can it be lightning? Can it be a volcanic eruption? So they redid the experiments, taking the critics' comments into consideration, and then they provided it with a ultraviolet radiation source, and it created the same again. So what they determined is, it doesn't matter which let me rephrase this, which different early elements they used, or even which source of power they used. Eventually, the experiment created basic amino acids, which is the building blocks of life as we know it. So that showed how life on Earth could have started. So here we can show the basic elements. So you have your different elements, molecules, and it forms a carbon chain. And these carbon chains are called amino acids, and different amino acids forms proteins. So these are the building blocks. So that's how the life on Earth more or likely started. So when the first reproducing molecules formed here on Earth or in space, the important thing is that they could have formed by natural processes. Scientists now know enough about those processes to feel confident about them, even though some of the steps remain unknown. And the details of the origin of the first cells are unknown. The structures of cells may have arisen automatically because of the way molecules interact during chemical evolution. If a dry mixture of amino acids is heated, the acids form long protein-like molecules that when poured into water collect to form microscopic spheres that behave in ways similar to cells. They have a thin membrane surface, they absorb material from their surroundings, they grow in size, and they divide and bud as the cells do. However, they contain no large molecule that occupies itself, so they are not alive. The first reproducing molecule to be surrounded by a protective membrane, resulting in a first cell, would have gained an important survival advantage over the other reproducing molecules. Biologists inferred that first cells must have been simple, single-celled organisms similar to modern bacteria. And as you learned with radioactive ages of 3.5 billion years and living stromatolites still from places today, stromatolites and other photosynthetic organisms would have begun adding oxygen, a product of photosynthesis, to Earth's early atmosphere. An oxygen abundance of only 0.1% would have created an ozone screen protecting organisms from the sun's ultraviolet radiation and later allowing life to colonize the land. Over the course of eons, the natural process of evolution gave rise to stunningly complex multicellular life forms with their own widely differing way of life. It is a common misconception to imagine that life is too complex to have evolved from such simple beginnings. It is possible because small variations can accumulate, although that accumulation requires great amount of time. There is little evidence of anything more than simple organisms on Earth until about 540 million years ago, almost 3 billion years after the earliest signs of life, at which time fossils indicate that life suddenly developed into a wide variety of complex forms such as the tribolites. The sudden increase of complexity is known as the Cambrian explosion and marks the beginning of the Cambrian period. If we represented the entire history of Earth on a time scale, the Cambrian explosion would be near the top of the column as shown in figure 20.7. The emergence of most animals familiar to you today, including fishes, amphibians, reptiles, birds, and mammals, would be crammed into the topmost part of the chart above the Cambrian explosion. So here we can see how everything developed on Earth. So here we can see is the ocean-like only and the age of mammals on top and the time scales we are talking about. So if you magnify the portion diagram as shown on the right side of figure 20.7, you can get a better idea of when these events occurred in the history of life. Humanoid creatures have walked on Earth for about 4 million years. This is a long time by the standard of human lifetime, but it only makes a narrow red line at the top of the diagram. All of the recorded history would be a microscopically thin line at the very top of the column. To understand just how thin that line is, imagine that the entire 4.6 billion year old history of the Earth has been compressed into a year-long video and that you began watching this video on January 1. Recall that in section 2 of chapter 1, you compare the history of the universe to the length of a football field. You would not see any signs of life until March or early April. And the slow evolution of the first simple forms would take the next 6 or 7 months. Suddenly in mid-November, you would see the tribolites and other complex organisms of the Cambrian explosion. You would see no life of any kind on land until November 28. But once life appeared, it would diversify quickly, and by December 12, you would see dinosaurs walking the continents. By the day after Christmas, they would be gone, and mammals and birds would be on the rise. If you watch closer, you might see the first humanoids form by late afternoon on New Year's Eve. And by late evening, you would see humans making the first stone tools. The Stone Age would last until 1159. after which the first towns and then cities would appear. Suddenly things would begin to happen at lightning speed. Babylon would flourish, the pyramids would rise, and Troy would fall. The Christian era would begin 14 seconds before the new year. Rome would fall, the Middle Ages and a Renaissance would flicker past. The American and French revolutions would occur 1.5 seconds before the end of the video. By imagining the history of Earth as a year-long video, you have gained some perspective on the rise of life. Tremendous amounts of time were needed for the first simple living things to evolve in the oceans. As life became more complex, new forms arose, more quickly as the hardest problems. How to produce, how to take energy efficiently from the environment, how to move around were solved. By the process of biological evolution, the easier problems like what to eat, where to live, and how to raise young were managed in different ways by different organisms, leading to the diversity that is seen today. Intelligence that appeared to set humans apart from other animals may be a unique solution to an evolutionary problem posed to humanity's ancient ancestors. The smart animal is better able to escape predators, catch its prey, and feed and shelter itself and its offspring. So under certain conditions, evolution is likely to naturally select for intelligence. So could there be carbon-based life elsewhere in the solar system? As you learned earlier, liquid water seems to be a requirement for carbon-based life, necessary both as the medium for vital chemical reactions and to transport nutrients and wastes. It is not surprising that life developed in Earth's oceans and stayed there for billions of years before it was able to colonize the land. It is difficult to pin down a range of environments and be sure that life based on carbon and water cannot exist outside those conditions. As long as there is occasionally some liquid water present, life has been found on Earth in places previously judged inhospitable, such as the bottoms of ice-covered lakes in Antarctica, far underground inside solid rock, and in pools of nearly boiling hot water. An organism that can survive and even thrive in extreme environments is called an extremophile. Scientists searching for life on other worlds must keep in mind Earth's extremophiles and the harsh conditions in which they thrive. So here we can see colonies of thermophilic, so heat-loving single-celled organisms thrive around the edge of Yellowstone's Natural Park's Grand Trisomic Spring at temperatures of 72 degrees Celsius, producing the green pigments. The blue water in the center of the pool is too hot even for thermophiles. So many worlds in the solar system can be eliminated immediately as hosts for water-based life because liquid water is not possible there. The Moon and Mercury are airless, and water would boil away into space immediately. Venus has traces of water vapor in its atmosphere, but it's too hot for liquid water to survive on the surface. The Jovian planets have deep atmospheres, and at certain altitude, it is likely that water condenses into liquid droplets. However, it seems unlikely that life would occur there. The Jovian planets do have solid surfaces, so look back at chapter 18, section 1. The isolated water droplets cannot mingle to mimic the original oceans on Earth, where organic molecules grew and interacted. Additionally, powerful downdraft currents in the atmosphere of the giant planets would quickly carry any reproducing molecules that did form there into inhospitably hot lower regions. As you learned in chapter 18, section 2, at least one of the Jovian satellites could potentially support life. Jupiter's moon, Europa, appears to have liquid water ocean below its icy crust, and minerals dissolved in the water could provide a source of raw material for chemical evolution. Europa's ocean is kept liquid now by tidal heating. There are evidentially also liquid zones inside Ganymede, Callisto, and Saturn's moon Enceladus that can change. These moons interact gravitationally with each other and their orbits change. All of them may have been frozen solid at other times in their histories, which would probably have destroyed any living organism that had developed there. Saturn's moon Titan is rich in organic molecules. You learn in chapter 18, section 3 that sunlight converts the methane in Titan's atmosphere into organic smog particles that settle to the surface. The chemistry of life that could have evolved from those molecules and survive in Titan's lakes of methane is unknown. It is fascinating to consider possibilities, but Titan's extremely low temperature, that's a typo. Both of these, I'm not exactly sure what those should be, but that is definitely wrong, would make chemical reactions so slow that life processes seem unlikely. Water containing organic molecules have been observed venting from the south polar region of Saturn's moon Enceladus. So look back again to chapter 18, section 3. It is possible that life could exist in that water under Enceladus crust, but the moon is quite small and its tidal heating might operate only occasionally. Enceladus might not have had plentiful liquid water for the extended time necessary for the rise of life. Aside from Earth, Mars is the most likely place for life to exist in the solar system because, as you learn in chapter 17, section 3, there's a great deal of evidence that liquid water once flowed on its surface. Even so, results from searches from signs of life on Mars are not encouraging. The robotic spacecraft Viking 1 and Viking 2 landed on Mars in 1976 and tested soil samples for living organisms. Some of the tests had puzzling, semi-positive results that scientists hypothesized were caused by non-biological chemical reactions in the soil. No evidence clearly indicates the presence of life or even of organic molecules in the Martian soil. Life may be required special circumstances to start on Earth, but once it started, biological evolution allowed life to spread across Earth and adapt to a wide range of conditions. Evidently, all niches, even extreme environments, became occupied. Scientists generally think this means that if life began on a planet, even if the environment of the planet later becomes generally inhospitable, as seems to have happened on Mars, some life could continue to survive. If life still exists on Mars, it may be hidden below ground, where there may be liquid water and where UV radiation from the sun cannot penetrate. There was a splash of news stories in the 1990s regarding supposed chemical and physical traces of life on Mars discovered inside a Martian meteorite found in Antarctica. Scientists were excited by the announcement, but they employed professional skepticism and immediately began testing for evidence. The results suggest that unusual chemical signatures in the rock may have formed by processes that did not involve life. Tiny features in a rock that were originally thought to be fossils of ancient Martian microorganisms could possibly be non-biological mineral formations instead. So here we can see a lander on Mars, and here we can see the rock that landed in Antarctica. In 2009, astronomers observing the Martian atmosphere announced detection of faint traces of methane, a substance made abundantly by living things on Earth. Methane would be destroyed in the Martian environment by solar UV radiation and chemical reactions. So the methane that is present must be produced recently. Question. So how will be assessed on this chapter? It went from history to biology. So this is just an overview. So if you look at the mock test and mock memo, you will know how to be assessed. As we go throughout this chapter, I will also give hints on how I will ask these questions. Also in 2014, the Curiosity rover detected a brief increase in methane abundance at its location. There are also geological processes that can emit methane, but those processes are connected within volcanism. A map of the Martian atmospheric methane concentrations would show methane primarily in locations that are not volcanic provinces. It seems possible that organisms living in a Martian soil are making methane right now. This evidence regarding potential life on Mars remains highly controversial. Conclusive evidence of life on Mars may have to wait until the geologists from Earth looking for fossils can scramble down a Martian stream beds and crack open rocks, or drill into the soil seeking signs of metabolizing microorganisms. There is plenty no compelling evidence for the existence of life in a solar system other than Earth. Now research will take you to distant planetary systems. So could life exist in other planetary systems? And you already know that there are many different kinds of stars and that many of these stars have planetary systems. As a first step towards answering this question, you can try to identify the kinds of stars that seem most likely to have stable planetary systems and where life could evolve. If a planet is to be a suitable home for living things, it must be in a stable orbit around its sun. That is easy in a planetary system like our own. A planet's orbits in binary stars systems would be unstable unless the component stars are very close together or very far apart. Astronomers can calculate that in binary systems with stars separated by intermediate distances of a few AU, the planet should eventually be swallowed up by one of the stars or ejected from the system. Half the stars in the galaxy are members of binary systems, and many of them are unlikely to support life on planets. Moreover, just because a star is single does not necessarily make it a good candidate for sustaining life. Earth required perhaps as much as 1 billion years to produce the first cells and 4.6 billion years for intelligence to emerge. Massive stars that shine for only a few million years do not meet this criterion. If the time for development of life on Earth is typical, then stars more massive and luminous than about the spectral F5 last too short of a time for complex life to develop. So main sequence stars of type G, K, and M are the best candidates in terms of stellar lifetime. The temperatures of planets is also important, and that depends on the type of star it orbits and the distance from the star. Astronomers have to find a habitable zone. I prefer the term Goldilocks zone around a star as a region within which planets orbit there have temperatures permitting the existence of liquid water. The Sun's habitable zone extends from near the orbit of Venus to the orbit of Mars, with Earth right in the middle. A low luminosity star has a small and narrow habitable zone, whereas a high luminosity star has a large and wide one. So I like to call it the Goldilocks zone because it's not too cold, not too warm, just right, as you think about the story of the three little bears. Stable planets inside the habitable zones of long-lived stars are the place where life seems to most likely. But given the tendency and resilience of Earth's life forms, there might be other seemingly inhospitable places in the universe where life exists. You should also note that 3 of the environments considered as possible havens for life is Europa, Titan, and Enceladus, are in the outer solar system far outside the Sun's conventionally defined habitable zones. So could intelligent life arise in other worlds? To try to answer this question, you can estimate the chances of any type of life arising in other worlds. Then assess the likelihood of that life developing intelligence. If other civilizations exist, it's possible humans eventually may be able to communicate with them. So nature puts restrictions on the place of such conversations. But the main problem lies in the unknown life expectancy of civilizations. So the first one is the travel between stars. So distance between stars are almost beyond comprehension. The fastest human device ever launched, the New Horizons probe, which took 9 years to reach Pluto and then sailed into the Kuiper Belt, will take about 90,000 years to travel the distance to the nearest star, which is 4 light years away. The obvious way to overcome these huge distances is with tremendously fast spaceships. Even the closest stars are many light years away. Nothing can exceed the speed of light, and accelerating a spaceship close to the speed of light takes huge amounts of energy. Even if you were to travel slower than light, your rocket will still require massive amounts of fuel. If you wanted to pilot a spaceship with a mass of 100 tons to the nearest star, and you traveled at half the speed of light, so as to arrive in 8 years, the trip would require 400 times as much energy as the United States consumes in 1 year. So imagine how much fuel the Starship Enterprise would need. So these limitations not only make it difficult for humans to leave the solar system, but they would also make it difficult for aliens to visit Earth. Reputable scientists have studied unidentified flying objects and have never found any evidence that Earth is being visited or has ever been visited by aliens. Humans are unlikely ever to meet aliens face to face. However, communications by electromagnetic signals across interstellar distances takes relatively little energy. Nature puts restrictions on travel through space, and it also restricts the possibility of communicating with distant civilizations by radio. One restriction based on simple physics: radio signals are electromagnetic waves and travel at the speed of light. And due to the distances between the stars, the speed of radio waves would severely limit humanity's ability to carry on normal conversations with distant civilizations. Decades could elapse between asking a question and getting an answer. So rather try to become a conversation, one group of astronomers decided in 1974 to broadcast a message of greeting towards globular cluster M13, 26,000 light years away, using a Arecibo radio telescope. When a signal arrives 26,000 years in the future, alien astronomers might be able to understand it because the message is anti-coded, meaning that it's intended to be decoded easily by beings about whom we know nothing except they built radio telescopes. The message is a string of 1,679 pulses and gaps. Pulses represent ones and gaps represent zeros. The string can be arranged in 2 dimensions in only 2 possible ways, as 23 rows of 73 or 73 rows of 23. The second arrangement forms a picture containing information about life on Earth. So this is the picture, and we saw that in that TED talk as well that has been sent out. So what are the chances that a signal like a Arecibo message would be heard across interstellar distances? Surprisingly, a radio dish the size of a Arecibo telescope, located anywhere in the Milky Way galaxy, could detect output from our Arecibo. So the human race's most technical capabilities already can put us in cosmic chat rooms. Although the 1974 Arecibo beacon was the only powerful signal sent purposely from Earth to other star systems, Earth is sending out many other signals more or less accidentally. Shortwave radio signals, including TV and FM, have been leaking into space for the last 60 years or so. Any civilization within 60 light years could already have detected Earth's civilization. That works both ways. Alien signals, whether intentional messages of friendship or the bladder of the equivalent to daytime TV, could be arriving at Earth now. Groups of astronomers from several countries are pointing radio telescopes and the most likely stars and listening for alien civilizations. So which channels should astronomers monitor? Signals with wavelengths longer than 30 centimeters would get lost in the background noise of the Milky Way galaxy, while wavelengths shorter than about 1 centimeter are mostly absorbed in Earth's atmosphere. And between those wavelengths is a radio window that is open for communication. Even this restricted window contains millions of possible radio frequency bands, and is too wide to monitor easily, but astronomers may have thought of a way to narrow the search. Within this broad radio window lie a 21 centimeter spectral line of net neutral hydrogen and an 18 centimeter line of hydroxyl. The interval between those lines has low background interference and was named the water hole because O plus OH hydroxyl yields water, H2O. Any civilization sophisticated enough to do radio astronomy would know of these lines and might appreciate their significance in the same way as do Earthlings. So here we can see this line. So here we can see background radiation, noise from the Milky Way, noise from Earth's atmosphere, the quantum mechanical noise, and here is that window that we call the water line or the water hole. A number of searches for extraterrestrial radio signals have been made and some are now underway. This field of study known as SETI, Search for Extraterrestrial Intelligence, and it has generated heated debate among astronomers, philosophers, theologians, and politicians. You can imagine that the discovery of real alien intelligence would cause a huge change in humanity's worldview, akin to Galileo's discovery that moons of Jupiter do not ground the Earth. Congress funded a NASA SETI search for a short time but ended support in the 1990s. In fact, the annual cost of major search is only as much as a single Air Force helicopter. But much of the reluctance to fund searches stems from issues other than cost. And segments of population, including some members of Congress, consider the idea of extraterrestrial beings as so outlandish that continued public funding for the search became impossible. Why do you guys think do governments and the public don't want to fund these searches? Fear is one of them, but there is a different reason as well, religion. What will it do to different religions? We talked about it a little bit, but yes, what would happen to different religions? And there's been nothing so far seems like a waste of money. Yes, but we still need to fund scientific projects even while we don't see results yet. But the biggest problem, especially politically, that they don't want to do these searches is religion. What will happen to religion? In spite of controversy, the search continues. The NASA SETI project, cancelled by Congress, was renamed Project Phoenix and completed using private funds. The SETI Institute, founded in 1984, managed Project Phoenix, plus several other important searches, and is currently building a new radioscope array in Northern California, in collaboration of the University of California, Berkeley, that was partly funded by Paul Allen, one of the co-founders of Microsoft. There's even a way for you to help with searches. The Berkeley SETI team, note that they are separate from the SETI Institute, with the support of the Planetary Society, has recruited about 4 million owners of personal computers that are connected to the internet. You can download a screensaver that searches data files from the Arecibo radio telescope for signals whenever you are not using your computer. So making use of this link, you can actually download SETI at home and participate in that as well. The search continues, but radio astronomers struggle to hear anything against the worsening babble of radio noise from human civilization. Wider and wider sections of the electromagnetic spectrum are being used for earthly communications. And this, combined with stray electromagnetic radiation from electronic devices, including everything from computers to refrigerators, makes hearing faint radio signals difficult. It would be ironic if humans failed to detect faint radio signals from other worlds because our own world has become too noisy. One alternate search strategy is to look for rapid flashes of laser light at optical or near-infrared wavelengths. Such extraterrestrial signals, if they exist, would have the advantage of being easily distinguished from natural light sources, but the disadvantage of being blocked by interstellar dust. Ultimately, the chance of success for any of the searches depends on the number of inhabited worlds in a galaxy. So question. So they are afraid some scientific discoveries may prove some religious beliefs incorrect. Yes, that is correct. So if you look at the course of history, most of scientific enhancement and progress were blocked by religions. For example, that the Earth was not a center of the universe and Earth revolved around the sun. That was blocked by the Roman Catholic Church for many, many years. If you look about where our modern maths comes from, our modern math comes from the Middle East, hence the word Arabic numerals. And in the 14 and 1500s, most of the mathematical and scientific breakthroughs that happened occurred in the Middle East. But then something happened in the Middle East, especially with the Prophet Muhammad, and there was a revolution, and then after that, all scientific works has been seen from the devil, and since then there have basically been no scientific or mathematical growth in the Middle East, and that is still going on today. So yes, a lot of things that happen and usually block science is people's personal beliefs regarding science, their beliefs regarding science and religion. So that is why it is important, and South Africa got that right, that there is a separation between church and state. But in some places around the world, people are still struggling with that. So how many inhabitable worlds are there? And this is a hint and a tip for you guys. This is a question that I always ask in the exam. Did you guys get that hint? So I always ask this question in the exam. This is of the work we're going to do now about the Drake equation. So one thing we can use to determine how many life or possible inhabitable worlds and how many possible civilizations there are is the Drake equation. And for the exam, I usually ask you guys to list the Drake equation, explain to me what the Drake equation is used for, and then also describe what each of these variables in a Drake equation is. So you have to know this equation by heart, because I will ask you what is the Drake equation, then you have to write down this equation, and you have to explain to me what a Drake equation is used for, and then describe or explain what each of these variables are. You guys happy with this hint? Awesome. So this equation was developed by Frank Drake. He was an astronomer at the Green Bank Observatory and is also one of the founding fathers of SETI. And he's done a lot of work. So if you ever get a chance to visit the Green Bank Observatory, one of their lounges is called the Drake Lounge after Frank Drake, and he has on top of the lounge's door, and in the lounge, a big plank with the equation on. So Frank Drake, I think, if I'm now speaking on a correction, he passed away in 2022. But what this equation means is, if we look at pure statistics, Then we have N is the number of stars. So NC will be the Drake equation, and that will be the number of civilizations we can communicate with. NC. So when we break down this equation, N is the number of stars in our galaxy. FP represents the number of those stars that have planets. The factor NHZ is the average number of habitable planets in each planetary system. So that means how many stars there will be inside their habitable zone that also contains liquid water. So the next part of the equation is FL. And that is the fraction of those planets where life begins. Fi is the fraction of those planets where life evolves into intelligence. And then Fs, that can also be replaced with L, is the lifetime of those civilizations, meaning how long will those civilizations last. And if you plug numbers into those equations, we can get an upper bound and a lower bound of how many possible civilizations there are. So the 6 factors on the right-hand side of the Drake equation can be roughly estimated with decreasing certainty as you proceed from left to right. The final factor is extremely uncertain. So Fs or Fl is the fraction of the star's life during which an intelligent species is communicative. So if a society survives at the technological level for only 100 years, the chances of communicating with it are small. If most civilizations last only a short time, there may be none capable of transmitting during the cosmologically short interval when Earthlings are capable of building radio telescopes to listen for them. On the other hand, a society that stabilizes and remains technologically capable for a long time is much more likely to be detected. For apparent stars with a span of 10 billion years, Fs might convincingly range from 10 to the power minus 8 if societies are extremely short-lived, to 10 to the power minus 3 if societies nor survive for 10 million years. So table 20.1 summarizes what many scientists consider a reasonable range of values for Fs and the other factors. If the optimistic estimates are true, there could only be a cumulative civilization within a few tens of light years from Earth. On the other hand, if pessimistic estimates are true, Earth may be the only planet that is capable of communication within thousands of the nearest galaxies. So here we can look at pessimistic and optimistic results. And you can plug these values into the equation and you can get a number. So when you look at NC, when you look at pessimistic, it's 2 times 10 to the power minus 4. If you look at optimistic, that's 1 times 10 to the power 8, which is quite big. So that, ladies and gentlemen, was this lecture. And also, ladies and gentlemen, this was this module. Do you have any questions? So I would just like to take this opportunity to thank you guys for the semester. It's been a great semester. I enjoyed working with you guys. So I just want to say thank you for you online now. I know you're also the same people in my class as well in person. So I enjoy the effort you're making to participate in my classes. I should have your semester marks ready by the end of this week. For the exam is scheduled on the 20th of June at 11:15 to 1:15, so a 2-hour exam. And the venue will be the Rotenbach Hall. I will make an announcement for that as well. So yes, on winter solstice. So that is a very good coincidence. I will, during this week, also open up a poll for you guys just to vote for 2 dates and times that we can schedule recap sessions. So we're going to have the lecture that is yes. So is there only one quiz for the semester? Yes, only one quiz for the semester. So yes, I'm going to open up a poll that you guys can vote for 2 recap sessions or revision sessions that we can schedule that you guys can use to ask questions, or if you want me to explain different work as well. Otherwise, thank you for everything. Have a wonderful day. Good luck finishing off the rest of your modules. Good luck with the exam. And if you have any questions, please feel free to email me. And don't be strangers. If I'm on campus and I'm in my office in the physics department, you guys are more than welcome to pop by anytime. Otherwise, thank you for everything and have a wonderful day.